Good evening, everyone. Hope you are doing very well. As you all know, that today we are going to cover our chapter Chemical Kinetics Theory, Part 5. Right? So, let's start with our today's topic, which is NCRT Chapter 3 Chemical Kinetics Theory, Part 5. NCRT Section 3.3.3. Today we are going to cover the NCRT Section 3.3.3. Before we start, I just want to mention that try to make this session interactive as much as you can, and if you are having any doubt in between the lecture, you can ask out that in the chat box. Okay, let's start. So, this is a disclaimer. Let's begin with today's objective. After attending this lecture, you will be able to derive the integrated rate equations for zero and first order reactions. What are the topics that we are going to be covered as per the NCRT? They are, the first is the subsection 3.3.3, which comes under the section 3.3 in the chapter Chemical Kinetics in our NCRT textbook, and the subsection is half-life of a reaction. In this, firstly, we will talk about the pseudo first order reaction. Then we will see the illustration of pseudo order reaction. Then we will see that what is half-life of a reaction. Then we will talk about the half-life for the zero order reaction, which we have covered the first type of the order of the reaction, which is zero order. Then for half-life for first order reaction. Then we will see the integrated rate laws for the reactions of zero and first order. Then we will learn some methods of determining the order of the reaction. Then we will see the use of differential rate expressions and the uses of integral rate expressions. And then we will see that what is half-life method, isolation method, and then we will practice some examples from 3.7 to 3.8. Lastly, we will see some text question from 3.5 to 3.6, and then we will see the summary which we covered, which we will going to cover in this lecture. And lastly, we will talk about the key points to remember as we studied in this lecture, right? So let's begin. So let's begin with the first topic, which is subsection 3.3.3, half-life of a reaction, in which let's study first of all about the pseudo first order reactions. What are these? Why we are calling them pseudo? So pseudo means something is a copy or similar to kind of, that thing before which the pseudo word is there. So order of a reaction is sometimes altered by the conditions. If any reaction has some order, it can be changed, it can be altered by the external conditions. Reaction which behave as first order, although they are of higher order, are called pseudo first order reaction. So what are we calling the pseudo first order reaction as? Those reactions who behave as first order, but although they are of higher order in actual. So we call them as pseudo first order reaction. That means they are not the first order reaction, but they kind of look like the first order. That's why the name says pseudo first order reactions. Hydrolysis of ethyl acetate, which is a chemical reaction between the ethyl acetate and water, because hydrolysis is the process of reaction of water molecule with the another compound. So when you are doing the hydrolysis of ethyl acetate, that means you are reacting the ethyl acetate with water, and this chemical reaction is an example of the pseudo first order reaction. In reality, it is a second order reaction, and the concentration of both ethyl acetate and water affect the rate of the reaction. So in the reality, if you talk about the ethyl acetate hydrolysis reaction is of second order reaction, but uh, the concentration of both ethyl acetate and water affect the rate of the reaction, due to which it changed and kind of look like first order. Water is taken in the large excess for the hydrolysis in this process of hydrolysis of ethyl acetate. Therefore, the concentration of water is not altered much during the reaction, because something, if it is limiting, if the concentration is limiting, then it can consume the first and then it can alter the rate of the reaction. But if something is already in the large excess, like the water in the hydrolysis process of ethyl acetate, then it will not going to alter much during the reaction. The rate of reaction is affected by the concentration of ethyl acetate only, because two compounds are there only which are reacting with each other, water and ethyl acetate. So if water is in the large excess, it will not going to affect, or concentration of water not going to alter much during the reaction, but the rate of reaction is affected by the concentration of the rest compound, which is the ethyl acetate only. Inversion of cane sugar is another pseudo first order reaction. Inversion of cane sugar is also the example of pseudo first order reaction. So if you see the reaction, how it seems: C12H22O11 plus water molecules. So cane sugar hydrolyzes, and you are doing the inversion of this. So this cane sugar structure will become the glucose structure and the fructose structure. Both structure have similar molecular formula C6H12O6, but the structurally they are different, glucose and fructose. So the rate for this reaction is K, that is rate constant, multiplied by the concentration of the reactant, that is of the cane sugar C12H22O11. Now if you look at this is kind of look like a first order reaction, right? Because only one power is there for the reactant, but it is not the first order. It is a pseudo first order reaction, because the water molecule, that is this water molecule presence in the large excess as compared to the presence of the cane sugar is going to affect the rate of the reactions, which will going to change the concentration of the reactant, which will going to affect the rate or order of the reaction. Okay, now let's illustrate the pseudo order reactions. That what are these, why we are talking about these. So consider the hydrolysis of ethyl acetate. We have seen the example, we have taken the example, not seen. So consider the hydrolysis of ethyl acetate, which is a chemical reaction between the ethyl acetate and the water molecule. So in the reality, it is a second order reaction, and concentration of both the ethyl acetate and water affect the rate of the reaction. Okay, so it is of a second order, but it is kind of look like first order. That's why we are calling it as a pseudo order reaction. Now water is taken in the large excess for the hydrolysis. Therefore, concentration of water is not altered much during the reaction, right? Because in this reaction, we are taking water in the larger excess as compared to the ethyl acetate. That means the concentration of water is so much to react with the ethyl acetate that the concentration of water is not going to change during the reaction that much as compared to the concentration of the ethyl acetate. Now if you look at this ethyl acetate, that is CH3COOC2H5, when it is reacting with the water molecule in the excess amount, it is converting to the acetic acid CH3COOH and ethanol C2H5OH. Now at time t is equals to 0, we have given the concentrations of the reactants and the products. The product concentration will be going to be 0 mole and the reactant concentration are going to be 0.01 mole and 10 mole for the water, because it is in the large excess as compared to the ethyl acetate, right? You can also see that it is only 0.01, but the water molecule is 10 mole. As compared to the ethyl acetate concentration, it is really large. Now at some time t, the ethyl acetate concentration becomes 0. It is already consumed. That means it is a limiting reagent in this reaction. So it is already consumed full. The water molecules that are going to left will be 9.99 moles. Still they are very much present, and the formation of the compound will depend on the limiting reagent, that is ethyl acetate. So the formation of the both the product concentration will be 0.01 mole and 0.01 mole respectively for the ethanoic acid and ethanol. Rate of the reaction is affected by the concentration of ethyl acetate only, right? Because in the rate law, in the rate expression, we only consider the relationship between the rate and the concentration of the reactant. Here in this reaction, the reactant is CH3COC2H5, that is ethyl acetate. So the rate of reaction is affected by its concentration. So during the example of example, if you are taken, so during the hydrolysis of 0.01 mole of ethyl acetate with the 10 mole of water, the amount of reactants and the products at the beginning t equals to 0 and the completion of the reaction, that is t equals to t of reaction, are given as like this, right? So this is the description, and you can clearly see that as the ethyl acetate is properly consumed as compared to the another reactant, that is water molecule, so the concentration of water will not going to affect that much. That means the only thing that is going to affect the rate will be the ethyl acetate concentration, which is diminishing properly after the completion of the reaction. That means at t equals to 0 to t equals to t, right? Okay, so it is kind of, you can say, not possible that a first order reaction will show the characteristic of second order, but in the pseudo order reactions, yes, it is possible that the reaction is the second order actually, but it will show the characteristic of first order, or the property similar to the first order, or the rate law similar to the first order, and that's why we are confusing between that whether it reaction is first order or second order. That's why this names comes, that let's call this a pseudo first order reaction, because it is looking or showing the properties like the first order reaction, but it is actually a second order. That's why the names comes. Okay, so this is the case. Okay, now let's talk about the next topic, which is half-life reaction. So what is half-life of a reaction? The half-life is the time. Name has already half in that. Okay, right? Half-life. So it is the time which is required for the concentration of reactant to decrease by half. So total life means the concentration of reactant is present for how much of time it is living, it is there. That is called life. But half-life means that when the concentration of reactant is decreasing by half directly, that is considered as half-life. That in how much time the concentration of the reactant is decreasing by half, that is considered the half-life of that reactant. Now how you represent it? It is represented by T half. Half is in subscript of the T. So this is the representation for the half-life of a reaction. Half-life of a reaction is inversely proportional to the initial concentration except for the first order reaction. If you remove the first order reaction, other than that, the half-life of a reaction generally is inversely proportional to the initial concentration. Initial means that at t equals to 0, what is the concentration of the reactant at the initial time, right? So half-life is inversely proportional to initial concentration. That means if the initial concentration is larger, the half-life will be smaller, and if the initial concentration is smaller, the half-life will be larger. Okay, so that's the kind of case except for the first order reaction. The general formula, which is not applicable to the first order reactions, is given as K times T half is equals to 1 upon 1 minus N multiplied by 1 upon A concentration to the power N minus 1. Okay, T half is representing the half-life of a reaction. A is representing the concentration of reactant, right? Now, beside the half-life, we also have other time periods like T90%, right? If you can calculate the half-life time period, let that how much time the concentration of reactant is taking to decrease by half, you can also count the other time periods like T90%. That means when the concentration of the reactant becomes 90% reduced, or it decreased by the 90%, then that time period is called as T90%. So you can also consider that or also calculate that beside the half-life. So by T90%, we mean that 90% of reactant is consumed and 10% of reactant is left. So this T90%, as I said, is showing that 90% of the reactant is already consumed in the reaction and only 10% of reactant is left. And the time which the concentration of the reactant taken to decrease by the 90%, that time we called as T90%. Okay. Now let's see the half-life for the zero order reaction. So for a zero order reaction, the rate constant means K, is given by K is equals to R naught minus R by T, right? So this is the reaction, or this is the relation we have already studied, we have already seen in our previous lecture. So K, that is rate constant, is given by the initial concentration of the reactant, which is represented by R naught, minus the final concentration of reactant R, divided by the time taken in this change of the reactant concentration. Okay, this is in the case of zero order reaction. So at the T equals to T half, that means when the time becomes T half, what does that mean? That the present concentration of the reactant at the T half is become half of the initial concentration of the reactant. Okay, so at T equals to T half, the reactant concentration become half of the initial concentration of the reactant. So the rate constant at the T half becomes K is equals to R naught minus R will become half of R naught. So half of R naught divided by T is we are taking as T half. Okay, so this is the relation of the rate constant at T half. Now from here you can see that T half will be going to be equals to, this T half will go here in the left hand side, K will here come at the denominator, and when you take the LCM in the numerator, here comes the 2R naught minus R naught upon 2 T half, right? So 2R naught minus R naught will be 1R naught, so R naught by 2, K will be here in the denominator. So T half, that is half-life for the zero order reaction, become equals to R naught by 2 times K, rate constant. Now it is clear that the T half or half-life for a zero order reaction is directly proportional to the initial concentration of the reactants and inversely proportional to the rate constant. Now from this relationship, you can clearly see that the T half, that is the half-life period for a zero order reaction, is directly depending upon the concentration or initial concentration of the reactant and inversely proportional to or inversely depending upon the rate constant, that is K. Now let's see the half-life for the first order reaction. So for the first order reaction, we have seen that K is equals to 2.303 by T log of initial concentration of reactant upon final concentration of reactant. And let's say this is NCERT equation marked as 3.15. Okay, in the NCERT textbook. So for the first order reaction, this is the K, that is the rate constant value. Now at T is equals to T half, that means when time becomes half lifetime, the R, that is the concentration of the reactant, will become the half of the concentration of reactant at initial, right? So at T equals to T half, R will become R naught by 2. This is NCERT equation 3.16. So the above equation, which is 3.15, will become K is equals to 2.303 by T half. So at T half, the equation 3.15 will be 2.303 by T half log R naught upon R will be R naught by 2. So R naught by 2. This 2 will go in the numerator. R naught will go to cancel out. Here log 2 will come. So T half will be 2.303 by K log 2. This is the T half for first order reaction. Now T half will be 2.303 by K log 2, as I said. So T half you can also write, you can also put the value of log 2, logarithmic 2 from the logarithmic table. So which is 0.301. So T half, that is half life, will become equals to 2.303 divided by the K multiplied by 0.301. Now when you multiply this term of or value of log 2 with 2.303, it will coming out as 0.693 divided by K rate constant. So T half for the first order reaction is 0.693 divided by K, and this is the NCERT equation marked as 3.17. It can be seen that for a first order reaction, the half-life period is constant. Right, half-life is constant because it is a rate constant and it is a constant value 0.693. So for a first order reaction, half-life period is constant. That it is independent of the initial concentration of the reacting species. That means the half-life is not depending upon the reactant initial concentration, and the half-life of first order reaction is readily calculated from the rate constant and vice versa. So if you know the rate constant value for the first order reaction, you get to know the half-life of the reaction also. Now let's see the table marked as 3.14, which is showing the integrated rate laws for reactions of 0 and the first order. This is a table showing the order of the reaction, reaction type, differential rate law for each reaction, integrated rate law, straight line plot, half-life, and the units of the rate constant. So if the order is 0 for the zero order reaction, the reaction type is reactant is converting to the product. The differential rate law for this is dr by dt is equals to minus of k. Integrated rate law will be k times t is equals to r naught minus r. Okay, this is the integrated rate law. We just derived this in the previous lecture also from this differential rate equation of the rate law, right? So dr by dt is equals to minus k. So we integrate this. So dr integration will be the r naught minus r, because it should be from r naught to r you integrate it, and dt will go here minus kt, so it will become kt, right? So k dt integration will become kt. So that's how we got this integrated rate law. So you just have to take the integration at both the sides, and then you have to solve that for taking or for identifying the value of the I, the constant of integration. Remember, we have studied this in the previous theory part. So integrated rate law for the zero order reaction is kt is equals to r naught minus r. The straight line plot in this we consider was between the concentration of the reactant versus the time. The half-life for the first zero order reaction is r naught by 2k, and the unit of rate constant in the zero order reaction is concentration time inverse or mole liter inverse second inverse. Okay, similarly for a first order reaction, the reaction type is reactant converting to the product. The differential rate law for first order reaction is dr by dt is equals to minus kr. Now this is a differential rate law. When you integrate the both side, you get the integrated rate law, which is reactant concentration is equals to r naught e to the power minus kt, or kt is equals to ln r naught by r. So straight line plot was between the ln R versus T in the first order reaction. Half-life for first order reaction is ln2 by K, or 0.693 by K, and the units of K, that is units of rate constant, is time inverse or second inverse for the first order reaction. So this table is showing the integrated rate laws along with another information for the reactions of 0 and the first order. You can learn it and write it somewhere. It will be of very use. Let's see the methods of determining the order of a reaction. So order of a reaction is never known beforehand, though majority of the reactions are of first or of second order. So the order of the reaction is never known beforehand. So if you want to know the order of the reaction, it can't be known before already. Why? We will see that. And though the majority of the reactions are of first or second order, but the majority of the reactions generally are of either first or the second order reactions. So following methods are the common methods used for determining the order of a reaction. What are those? Firstly, use of differential rate expression. So first of all, you should know that how to determine the differential rate expression from the rate law of a particular reaction. Secondly, use of integral rate expression. Then you have to know about the conversion of differential rate expression to the integral rate expression via integration. Okay. Thirdly, the half-life method. You should know that like half-life method will going to be used to determine the order of the reaction, because that will determine whether the half-life is how much, right, and whether it is depending upon the initial concentration of reactant or not. That will also kind of helps us to determine the order of a reaction. Fourth was isolation method. So fourth is isolation method, the fourth method which commonly used for determining order of reaction. Use of differential rate expression. So the first method was use of differential rate expression. So according to the method differential rate expression, which was devised by the Van 't Hoff, the rate of an nth order reaction is given by. So basically this method differential rate expression, which is given by Van 't Hoff, he said that the rate for an nth order reaction, that means the order is not particularly known, let's suppose it is nth order, for the rate of that nth order reaction, it is given by rate is equals to knc to the power n. N is the nth order, k is the rate constant, and r is representing the rate of a reaction. Now taking logarithm, you have to take the logarithm of both sides. So we have log, or you can say ln r is equals to ln kn plus n ln c. Here we just put the properties of the ln or log. Okay, so if two terms are in the multiplication and you take the log of both, you can write it as log of a term plus log of b term. Now log of b term means log of c to the power n. Now something, if it is present in power, it will go in the product form in the log. So n is already in the power, so n will go here from power to the product. So the ln r will become equals to ln kn plus n ln c. If the double logarithmic plot of rate versus concentration gives a straight line, then the slope gives the value of n and intercept gives the value of ln kn. Okay, ln is basically the logarithmic term which you can find out in the mathematics also easily, and it has a different values, it has proper table, so you have to learn that and then you can apply it here. So what we are saying, that if double logarithmic plot of rate versus concentration, it will give a straight line, then the slope of that graph gives the value of the n, that is order, and intercept, which is coming on the y-axis, gives the value of ln kn, that is this term. Okay, so when you know this term, when you know n, the ln C will remain and ln R will remain. Okay, but when you plot the rate versus the concentration graph, it will give a straight line. Straight line means you can get a slope which is basically representing the n, and the intercept on the y-axis is representing the value of ln kn. Use of differential rate expression. Now, if R1 and R2 are the rates at two different reactant concentrations. Okay, R is representing the rate. Now, let's say we are considering the two concentrations C1 and C2 at which the two rate are R1 and R2. Two different reactant concentrations C1 and C2. Then R1 by R2 is given by minus of dC1, that is the rate of change of concentration of 1 divided by the rate of change of concentration of 2, minus dC1 by dt minus dC2 by dt, right? So this will be equals to this rate will be equals to KnC1n divided by KnC2n, C representing the concentrations of the first and the second reaction, right? So Kn will get cancelled out, and the C1 by C2 will whole power n will going to be the equals to the R1 by R2. So if R1 and R2 are rates at two different concentrations C1, C2, then R1 is by R2 is equals to C1 by C2 to the power n, where n is representing the nth order of the reaction. Now taking the logarithm, if you take the log, ln of R1 by R2 is equals to n times ln of C1 by C2, right? This power will go in the product, where n is ln R1 by R2 upon ln C1 by C2. So when you find out the n value, it will be ln R1 by R2 divided by ln C1 by C2, right? N representing the order of the reaction. So what we are discussing, we were discussing about the method, which is use of differential rate expression method, in which how can you learn about that, how can you determine the value of n, that is the order of the reaction. So this is how you determine the n value, which is ln R1 by R2 upon ln C1 by C2. Let's see our next method, which is use of integral rate expressions. So this method can be used either analytically or graphically. Okay, so by two ways we can use this method. Either analytically, you can analyze the data, or graphically, you can graph the data and then you can analyze. So in the analytical method, we assume a certain order for a reaction and calculate the rate constant from the given data. So in the analytical method, what we do, we first of all, let's assume a certain order of the reaction and then we calculate the rate constant from the given data. The consistency of the k values obtained suggests that the assumed order is correct. Okay, now when you get the values of k, that is rate constant, after assuming a certain order of the reaction, that constancy of k values which you are going to obtain suggests that what will be the order, or whether our order assumed is correct or not. If the k values obtained are not constant, then we assume a different order and we repeat this process. Again, calculate the k values using the new rate expression and then see that if k is coming out as constant or not. If it is, then that means we are assuming a correct order. This is how you can get the order of the reaction using the integral rate expressions. Now, as you can see, this is a graph between the ln R and ln C, that is ln of rate and ln of concentration. There comes a straight line having slope n, intercept is ln kn. In the graphical method, basically, we plot the lnc versus lnr graph like this, which is a straight line, and the reaction is of the first order. Similarly, the integrated expression for the second order reaction can be utilized graphically to ascertain if the reaction is of second order and so. So, if you want to integrate, or if you want to use the integrated expression for the second order reaction, you can use it graphically to ascertain if the reaction is of second order or not. Now let's see our next method, that is half-life method. So what is half-life method? So if two experiments are carried out at different initial molar concentrations, so if we are carrying out two different experiments which are okay at different molar concentrations, so two experiments have have reactant having different initial molar concentrations, then T half 1 divided by T half 2 is equals to A2 by A1 whole power n minus 1, right? Or you can say ln T half 1 by T half 2 is equals to n minus 1 ln A2 by A1. Okay, so two experiments you have to carry out at different initial molar concentrations. So if you see the half-life for the two different molar concentration experiment, so T half of 1 representing the first experiment T half, and T half of 2 representing the second T half of the second experiment, this is going to be equals to A2 by A1 to the power n minus 1. Or you can also say that ln of T half 1 by T half 2 is equals to n minus 1 multiplied by ln of A2 by A1. And from here you can see that n, that is the order of the reaction, will going to be equals to 1 plus ln of T half 1 plus ln of T half 2 divided by ln of A2 by A1. Okay, so this is the expression you are going to get for the order of the reaction using the half-life method, where we are considering the T half for the two different molar concentrations, and then you find out the value of order. Our next method is isolation method. Okay, let's see what's in this. So sometimes the kinetics of a reaction are studied in the successive experiments by keeping the concentration of all but one reactant in large, so that the result gives the order with respect to the reactant whose concentration is changing significantly. So sometimes the kinetics of a reaction are studied, that means kinetics of a reaction, how it is functioning, what is the molar ratio we have taken. So sometimes kinetics of reaction is studied in successive experiments by keeping the concentration of all but one reactant in large excess. Okay, so that the result will give the order with respect to the reactant whose concentration is changing significantly. If any reactant is changing its concentration significantly, that means the rate will be going to determine by that reactant. Okay, so order will be going to determine with respect to that reactant concentration, which is going to change significantly after the successive experiments. Thus, synthesis of HI from hydrogen and iodine molecule is a pseudo first order reaction with respect to hydrogen in the presence of large excess of the iodine, and also pseudo first order with respect to iodine in presence of large excess of H2. So we are considering here an example that in the synthesis of hydrogen iodide from the hydrogen and iodine molecules is pseudo first order. So this reaction of synthesis of hydrogen iodide from H2 and I2 is pseudo first order with respect to the H2 molecule in presence of large excess of I2. Okay, and also the pseudo first order with respect to I2 in the presence of large excess of H2. Okay, so if H2 is in the large excess with respect to I2, we consider this reaction as a pseudo first order. And if we have a large excess of I2 with respect to H2, then this reaction will be going to be pseudo first order also. Okay, so the synthesis of HI from H2 and I2 is an example for the isolation method of the determining the order of the reaction. Hence, overall, it is a second order reaction. Okay, this HI synthesis from the H2 and I2. This is overall a second order reaction, but act as a pseudo first order. Okay, now let's do an example here, which is marked as 3.7. The example is that a first order reaction is found to have a rate constant K is equals to 5.5 times 10 to the power minus 14. Okay, so we have given a first order reaction. Okay, and its rate constant value is already given in the second inverse. Remember, you have to point out, or you have to take care of the units of the rate constant given in the questions, because that is going to help you a lot with to determine the order of the reaction. So you have to find the half-life of the reaction of first order reaction who's having the rate constant value as K is equals to 5.5 times 10 to the power minus 14 second inverse. So what will be the half-life of the reaction? You got some time, try to solve this, and then we will conclude to its correct answer. Okay, let's see. So for this given question, the solution will be, first of all, the half-life for a first order reaction you have to find out. So the half-life for a first order reaction is T half is equals to 0.693 divided by the rate constant K. This is the value of the T half, the half-life for first order reaction. And this is marked as NCERT equation 3.17. Now T half is equals to 0.693 divided by the rate constant is already given, 5.5 times 10 to the power minus 14 second inverse. The only variable here, the unknown is T half. Rest are the numerical values or the fraction. You just have to solve this. So T half will come out as 1.26 multiply by the 10 to the power 13 second. The second inverse go in the numerator, become second. So this is how the first order reaction half-life you can determine if you know the value of the rate constant of it. Now let's see the another example, which is marked as 3.8. Show that in a first order reaction, the time required for the completion of 99.9% is 10 times of half-life of the reaction. So you have to show that how in a first order reaction, time which is required for the completion of reaction of 99% is 10 times of half-life of reaction. You have given some time, try to analyze this, then we will see how you can show this, how you will be going to answer. Okay, let's see. So for this example, so when the reaction is completed 99.9%, okay, that means we have 0.1% left of the reaction remaining, right? Other than that, the 99.9% of the reaction is already completed. When this is the case, you can consider the reactant concentration, that is Rn, is equals to R naught, that is initial concentration, minus 0.999 times of R naught, right? That means from the initial concentration, the 0.999 times of initial concentration amount of the concentration is already subtracted. Okay, that is going to be our final, or that is going to be our present concentration of the reactant. Okay, you got it? Any doubt? So let me explain again that we have already given that our the reaction is 99.9% completed, right? So that means only 0.1% remains. If you remove the percent, this decimal will go backwards, so it will become 0.999. So if the reaction is completed this much percent, that means our final or the present concentration of the reactant will going to be equals to the initial concentration minus of the initial concentration multiplied by 0.999. Okay, so this is how you can get the present concentration of the reactant. And the K, the rate constant for a first order reaction is equals to 2.303 by T log of initial concentration upon final concentration. This is a NCERT equation marked as 3.15. Now 2.303 by T log R naught upon this R value is the present value of the concentration of reactant, that is R naught minus 0.999 R naught. So log of R naught upon R naught minus 0.999 R naught, this will be equals to 2.303 by T log of 10 to the power 3. Now how this comes? So R naught, you can see that both in the numerator and denominator is common. So when you take the R naught as common from the denominator, it will be R naught multiplied by 1 minus 0.999, right? And R naught will cancel out. 1 upon 1 minus 0.9 will become 0.1, right? Now 0.1 or you can say 0.001, right? That will go in the numerator, and 0.001 you can also write it as 10 to the power minus 3. So when it go in the numerator, it will become 10 to the power plus 3. That's how here the 10 to the power plus 3 came. Now 10 to the power 3. So 3 in the power. 3 will go here in the product. And log 10 is 1. So T is going to be equals to 6.909, that is 2.303 multiplied by 3, that is 6.909, divided by this K. This is equals to T, the time. Now for the half-life of the reaction, we have given that the time which is requiring for the completion of 99.9% is 10 times of half-life. So we have calculated the time in which the reaction is completed, 99.9%. Now half-life for the reaction is given as, for the first order, T half is equals to 0.693 by K. Right, now according to the question, T by T half is equals to 6.909 divided by K multiplied by K by 0.693, which is equals to 10. Right, yeah, that means T is equals to 10 times of T half. This is same, right? That T is the time representing for the completion of 99.9% of reaction. So this is T, which is given as equals to 10 times of half-life. So 10 multiplied by T half, right? Now you can write it as T by T half is equals to 10. And you know the value of T, which is this much. You know the value of T half, you can put it in the denominator. That means the equation will become kind of like this, right? And okay, and K will cancel out from here, and now this divided by this is going to be equals to 10. Okay, so what we are saying that we have to show that in the first order reaction, time required for the completion of 99.9% is 10 times of half-life, and that's how we can show that. Okay, so this is a proving question basically. So this is how you can prove that. First of all, you have to calculate the time for the completion of the reaction in the given percent by using the rate constant expression, and then you have to calculate the half-life for the same reaction, and then you have to equal or equate both the quantities you just find out according to the term or according to the condition as per the question. Okay, so this is how you can show that. Okay, now also let's practice in text question which is marked as 3.5. The question is saying that a first order reaction has a rate constant 1.15 times 10 to the power minus 3 second inverse. How long will the 5 gram of this reactant take to reduce to 3 gram? So we have given the rate constant value for a first order reaction, and also the question was that 5 gram of the reactant converting to 3 gram, how much time the reactant is taking to convert from 5 gram to 3 gram. This you have to find out. So you got some time, try to solve this, then we will see that what is the correct answer. Okay, let's see. So for this question, let's see that how you can calculate the time. So from the question, we can write down the following information which is already given, that the initial amount of the reactant is 5 gram. The final concentration of the reactant is 3 gram. The rate constant is 1.15 times 10 to the power minus 3 second inverse. And we know that for a first order reaction, the time you can calculate as 2.303 by K rate constant log R naught by R. Right? We know the R naught, we know the R, we know the rate constant value, so we can calculate the time. Right? So 2.303 by 1.15 times 10 to the power minus 3 log of 5 by 3. So only the unknown term is the time. You have to calculate that. So time will be 2.303 by 1.15 times 10 to the power minus 3 multiply by the log 5 by 3. Log 5 by 3 will be log 5 minus log 3. So that will be 0.2219, and you have to multiply these terms together to get the value of t as 444.38 seconds, which is equivalent to 444 seconds. Okay, so this is how you can calculate the time of changing of the reactant concentration if it is already given in the question. And also the rate constant is also given in the question. Okay, so this is how you can solve it. Okay, thank you so much for joining this session.